Okay, ladies and gentlemen, good day all. Today we are going to look at the uh, complex compounds or coordination compound. A compound sometimes, or coordination compounds are sometimes called coordination complex. So it means that the coordination compound, you can consider it as either coordination compound or the coordination complex. And this coordination complex contains two important components. And these two important components is central metal ion. We have central metal ion and the ligands. So in every coordination complex, when we are talking about coordination complex, you must actually put two things in your mind. One, the central metal ion and the ligands. The ligands it can be positively charged or negatively charged that surround the central metal ion. So that is why generally, if we are talking about coordination chemistry, as I said, two things are important. We have ligand and we have central metal ion. So we can now say this one is ligand 1, and this one it can be ligand 2, and this one it can be L3. So usually the central metal ion is surrounded by the ligands. And this ligand, it can be positive charge and it can be negative charge, or it can be neutral. So coordination compounds are like that. So the coordination complexes, we have a ligand that usually surround the central metal ion. So here our central metal ion is copper. And we have four different ligands that surround the central metal ion. And as I said, the ligand can be positive, they can be negative, or neutral. As we continue, we are going to look at how this ligand behave and how are they important to the central metal ion. So now, if a ligand is capable of forming more than one bond with the central metal atom or ion, then ring structures are produced, which are known as metal chelates. So the ring forming groups are described as chelating agents or polydentate ligand. So actually, as we are going to continue with the lecture, we are going to see different types of ligand. We have a ligand that form one bond, only one bond with the central metal ion, and we have ligands that can produce more than one bonding with the central metal ion. So those kinds of ligands that actually form a bond that can form more than one bond with the central metal ion, they produce a ring structure. So it means that when we have bidentate or tridental ligand, because bidentates are the ligand that donates 2 lone pair of electrons. They are the one that donates more than 2 lone pair of electrons. So those kinds of ligands, they form a ring structure. So as a result of that, they are called metal chelates. And those groups that are forming the ring, they are described as a chelating agents. They are described as a chelating agents. Then now, the coordination number, we have what we call coordination number. Coordination number of the central metal atom or ion is the total number of sides occupied by a ligand. Like for example, a bidental ligand uses 2 sides. Tridental ligand use 3 sides. So it means that in the case of bidental ligands, the coordination number is 2, and in the case of tridental ligands, the coordination number is 4. The coordination number is 4. So now let's just look at the examples of this. So in this case, we have like, for example, this is the compound. This is coordination compound. So now In this case, we are going to look at the charges as well as the coordination states of this compound and also the oxidation state. So how do we get it? It's simple. This is cobalt and this is chlorine. And chlorine usually have an oxidation number of -1 from the basics of chemistry. And this is nitrogen. That is, the charge of this nitrogen is also -1. And we have ammonia. And the charge of ammonia is 0. So it's nil. Ammonia doesn't have any charge. And of course, if you look at the coordinations where the coordination number is this brackets, that is the coordinations where we call it coordination pair. So now from there, if we are actually going to get the oxidation number, what are we going to do? Of course, we are going to get for cobalt. So therefore, cobalt will be considered as X. And then we have chlorine. And the charge of chlorine is -1. And then the charge of NO2 is also -1. And then the charge of ammonium is 0. So we are now going to set 0 times how many ammonia do we have here is 4. So we are now going to set everything because the coordination sphere and the coordination sphere, it has a net charge. And the net charge is +1. So at the end, after we add everything, then we are now going to set is equal to +1. But if there is nothing here, then we are going to set is equal to 0. But because we have +1, so that is why we end up of saying everything equals to +1. Then now, how do we do it? What we are going to do now is that -1 minus 1 is -2, and then we have plus 0 times 4. So everything is 0 because 0 times 4 is 0. Any number times 0 is 0. So therefore we have is equal to +1. So you see what we have here is almost exactly with what we have here. So therefore we have x minus 2 is equal to +1. Then we now take this -2 to the other sides. It's now going to be x is equal to +1 plus 3. And as a result of that, we have our oxidation number of cobalt in this compound as +3. And then how do we get the coordination number? Because all these elements, they are monodental ligands. It means that they donate only one pair of electrons. So they have one site of attachment. So now how do we do it? Then we count the number of the ligand because all of them, we have ammonia. Ammonia is monodental ligand. And how many ammonia do we have is 4. So it means that from ammonia, each ammonia donates one pair of electrons or have one site of attachment. So we have 4 ammonia. So therefore we have 4 sites of attachment from ammonia. Then we have nitrogen 4 oxide, that is also 1 attachment point. Then we have chlorine is also 1 attachment point. So we have 4 here. We have 4 here from ammonia. We have 4 from ammonia. Then we have 1 from nitrogen 4 oxide, and then we have also 1 plus chlorine. So we're now going to set 1 plus 1 plus 4. So at the end, we have 6. So the coordination number is 6. So ladies and gentlemen, I think it is very, very important in this structure. If you want to actually open it off very well, we understand that we have the central metal ion. And the central metal ion here is cobalt, which is considered no other way. The central metal ion are considered as a Lewis acid, while those ligands, they are considered as a Lewis base because they are donating lone pair of electrons. So you see, one ammonia here attach itself. That's 1 point of attachment because it is monodental ligand. So we have 1 here. Then we also have another ammonia here because we have 4. Then we also have another ammonia here. We also have another ammonia. You can also have another ammonia here. So it means that from here, there is 4 sites of attachment. So we have 4. And of course, we have chlorine. So the chlorine can actually occupy this space. Then we have nitrogen 4 oxide. Then we have NO2. So this is what we call uh, uh, coordination compound. The ammonia, the chlorine, nitrogen 4 oxide, they are all ligands because they occupy the central metal ion. And of course, the next thing is the coordination pair. And this is the coordination pair. This bracket is called coordination pair. And of course, we have plus 1 here. So this actually for the coordination chemistry. That is from the basic, from the very beginning. That number one, coordination compounds are compounds, or they are also considered as a coordination complex, and they are made up of two important components. And these two important components, we have central metal ion and the ligand. We have central metal ion and ligand. So now, okay, so now we are going to look at some examples of this ligand or this coordination complex. So in this coordination complex, what we are going to look at is actually, for example, now, this is a ligand. This is a coordination compound. And remember from the previous slide I talked about this coordination compound are made up of a central metal ion and a ligand. And the central metal ion is considered as a Lewis acid. So that is why here zinc, because it is a central metal ion and it is a Lewis acid, because generally from the basic knowledge of the of Lewis acid, that a Lewis acid are compound that accept lone pair of electrons. And then we have a Lewis base, and Lewis base are the ligand because they are the one that donate lone pair of electrons. So it means if you have an acid, if you have a compound, so definitely in that compound you can get your Lewis acid and a Lewis base. One must accept lone pair of electrons and the other one must donate lone pair of electrons. So the one that accept lone pair of electrons are the Lewis acid, and they are the central metal ion in the case of coordination compounds. And then we have the ligand. The ligand can be actually a compound from what I said that actually donate lone pair of electrons. So we have cyanide ion here, and the cyanide ion here is negative charge. So that is why I told you that this ligand, it can be positive ligand, it can be negative ligand. So we have classification of ligand on different bases. We can classify them based on their charges. So those that have positive charge, they are called positive ligand. Those that have negative charge, they are called negative ligand. And those that have no charge, they are called neutral ligand. So now, which actually atoms specifically donate lone pair of electrons in the cyanide? So it's carbon, and the coordination number is 4. And why the coordination number is 4? Because number one, cyanide have 1 point of attachment, and we have 4 cyanide here. So you now multiply 1 times 4, and that is how we arrive at coordination number of 4. And then we have platinum here, and we have the central metal ion here as 6. So now chlorine is the ligand, while platinum 4 plus is the Lewis acid, which is the central metal ion. So chlorine is a monodental ligand that donates 1 lone pair of electrons, or 1 point of attachment, and therefore the coordination number is 6 because we have 6 chlorine. And of course, then for the ammonia, ammonia also is monodental ligand, and it is a neutral ligand because it doesn't have any charge here. And the central metal ion is nickel, and the atoms that donate the electrons in the ammonia is nitrogen. And then the coordination number is 6. So now we are going to look at these different types of ligands. We are going to look at these different types of ligand on the basis of the point of attachment. So we have monodental ligand. So when ligand donate 1 pair of electrons to the metal atom, that type of ligand is called monodental ligand. An example of this monodental ligand, we have chloro, we have hydroxo, we have amine and methylamine. So all these are the examples of monodental ligands. Okay. So now the next thing is bidental ligand. So bidental ligand are ligands that actually that contain two or more atoms, and each of which can simultaneously form a two-electron donor bond to the same metal ion. So it means that in the case of bidental ligand, it's a group of atoms that donates two electron pair or two lone pair of electrons to the central metal ion. That is bidental ligand. And of course, from the previous slides, I told you that if you have a ligand that donates more than one lone pair of electrons, they actually tend form what we call they form what you call a ring structure. And that is why they are called chelating ligand, or they are called chelate ligands. So example of this bidental ligand, we have ethylene diamine, we have also oxalate, and ethylene diamine are all example of bidental ligand. And then the next thing is multidental ligand, or in the other way, you can actually call it polydental ligand. So polydental ligand are those kinds of ligands that will need so many number of electrons. And examples, we have dialene, diethyl, diethylene tetraamine. So diethylene tetraamine is tridental ligand. It's what? Tridental ligand. Why is considered as tridental ligand? Because it's actually donate only two lone pair of electrons. And we have EDTA. EDTA is ethylene diamine tetraacetic acid. Ethylene diamine tetraacetic acid, and it donates 6 lone pair of electrons. And that is why it falls under polydental ligands. Okay? So then we are now also going to look at the isomers. So before then, let's stop here, then we'll talk about the isomers in the next video. Okay.